Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering. In today's class, we are going to discuss about the two-port network interconnections. So in the previous class, we have discussed the two-port network interrelation, which means what is the relation between the various parameters. So the various parameters that we have discussed are ABCD parameters, Z parameters, Y parameters, and H parameters, and the interrelation between those parameters that we have discussed in the previous class. Now here we are discussing about the interconnection, which means if two or more networks, okay, so what are the various ways to connect these networks together, that we will discuss in today's class. So here, when coming to the, what is the need of connecting the various networks together? Of course, there are various reasons to get connected the various networks together. Okay, and the various types of interconnections of these two-port networks are: one is the series connection of the two-port network. So we already know what is meant by the series and what is meant by the parallel. Okay, so and another one is the parallel connection of the two-port networks. Then the third one is the cascade connection of the two-port networks. Then finally, there is another possible way to connect these two networks. One is series and parallel permissibility of the connection. So in this class, we will discuss one by one. So when we connect the two or more networks in series, okay, then what is the resultant network parameters? Okay, so that we will here discuss, and we will develop the relation between these two, because here, as you can see, the series connection is something like this, because the series connection is nothing but one common point in between the two networks. Okay, so this is what the series connection. Okay, which means here the second connection of the port 1 is connected to the what is that, the first connection of the port 1, and similarly here the second connection of the port 2 is connected to the first connection of the port 2. So in this way, this is the series connection. So here, as you know, there are two networks that are connected in series. One is ZA and ZB. Then let us consider here the resultant network is Z. So then what is Z equal in terms of ZA and ZB? So that we are going to define how we are going to derive the relation between Z and ZA and ZB, which means the resultant vector. So, or the resultant vector, let us consider here it is Z. Okay, so the Z also having again the two ports, right? Similarly, when coming to the parallel connection, so here this is the parallel connection. So which means here, let us consider here the 1 1 and 1 2, 2 1 and 2 2. Okay, so the same here also 1 1 1 2 2 1 2 2. So here this 1 1 is connected to this 1 1, and here this 2 1 2 is connected to the 1 2 of the second network, second network, and similarly this point is connected to this, and this point is connected to this, so that we can call it as this is a parallel network, right? Or the parallel connection between the two-port networks. Then in this case again, what is the resultant vector? The resultant what is the two-port network? Let us consider here it is Y. Then what is the relation between these two that we are going to derive here? Then the cascade connection, okay, which is nothing but just side by side, because the output terminals of the network 1 is connected to the input terminals of the network 2. Okay, so this is called the cascade connection. Then one by one we will discuss. First, let us go with the series connection of the two-port network, right? So here we have considered, of course, the best suitable parameters to make the series connection of these two-port networks is the impedance parameters, which are the Z parameter. So that's why here we are considered the Z parameters only. So here, let us consider here, this is a two-port network 1, here the network 1 or network A, and here it is network B. And here it is network B, right? So here the V1A and I1A are the, here this V1A and I1A are the input voltage and input current for the network ZA, and similarly here I2A and V2A are the output voltage and output currents of these network ZA and two-port network ZA. Then when coming to the ZB here, again here let us consider I1B and V1B are the input voltage and currents for the network ZB, and I2B and V2B are the output voltage and currents for the network ZB. Then let us consider here, of course this is connected in series, and then the input voltage between these two networks is, let us consider here it is V1, and similarly the output voltage for these two networks is, let us consider as a V2, and the network, and the input current for this resultant network, let us consider Z. Okay, so the input current, let us consider I1, and the output current is I2. So here for the resultant network, the input parameters are the V1, I1, and the output parameters are V2, I2. So now we are going to find the V1, V2 in terms of V1A, V1B, I1, and what is that, I2A, I2B, and also similarly I1A, I2A, and I1B and I2B. Right. So first, let us consider the networks independently and write the equations, because as we know these are the Z parameters, and for the Z parameters we will write the voltage equations in terms of the current, right? So first let us write in the form of matrix. Then for the first network here, the input voltage is V1A and the output voltage is V2A. So the V1A and V2A in terms of the input current I1A and the output current I2A for the network ZA, right? Then if you write this in terms of equation, then you will get V1A is equal to here Z11A into I1A plus Z12A into I2A, and this is, let us consider this is equation number 1. And similarly when coming to the second voltage equation, that is output voltage equation for the network ZA, so here V2A is equal to Z21A into I1A plus Z22A into I2A. So let us consider this is equation number 2. Then the same way here, let us consider for the network ZB and write the voltage and current, the input voltage and output voltage equations in terms of input current and output current for the network ZB. So then here, then coming to the equation number 3, which is V1B, which is the input voltage equation for the network B, and here V2B is the output voltage equation for the network B in terms of input current and the output current of the network ZB, right? So let us consider these are equation number 3 and equation number 4. So then now we know the condition for the series connection. Okay, so if these network 1 and network 2 are connected in series, is nothing but the current flowing through the series connection is same. So that's why here, so I1A and I1B which is equal to 0, so the same, because I1A is equal to I1B is equal to, let us consider here I1, so I1 is the current flowing through the resultant network. Then similar way, output side also, the I2A is the current flowing through the network ZA, and I2B is the current flowing through the network ZB, right? Then here I2 is equal to I2B equal to I2, right? Then, sorry, here I2A, here it is a printing mistake, I2A is equal to I2B is equal to I2, right? Then here, this is I2A. Then here, next thing, and again in terms of voltage, V1 is equal to V1A plus V1B, and V2 is equal to V2A plus V2B, because if voltages are connected in series, then the resultant voltage is the sum of the individual voltages, that we know already. So that's why here V1 is equal to V1A plus V1B, and V2 is equal to V2A plus V2B. So let us consider these are the equation number 6 and 7, right? So now actually what we are going to find, we should, because the resultant network is here it is, the input voltage and output voltage are V1 and V2, and the input current and output currents are what is it, I1 and I2. Okay, So here I am trying to write the voltage equations in terms of the currents, because here we don't know I1 and I2, but we know that I1 is equal to I1A and what is that, and I1 is equal to I1B. Similarly, I2 is equal to I2A is equal to I2B. Then here substitute the values of V1A and V1B from equation number 1, because here from the equation number 1 we know that V1A and V1B values into the equation number 6, because here equation number 6 is V1 is equal to V1A plus V1B, right? Then here V1 is equal to, just to substitute the values of V1A. So the value of V1A is Z11A into I1A plus Z12A into I2A plus, and here this V1B value is Z11B into I1B plus Z1 I2, I mean Z12B into I2B. So so here it is the value of, here it is V1A and here it is the value of V1B. I mean, this is from equation number, what is that, from equation number 1 and equation number, this is 3, right? So V1A and V1B value. Then similarly, then if you simplify this one, and again here substitute in the place of I1B, I1A and what is that, I1A and I1B, where it is I1B, yeah, I1B as a I1, okay, and I2A and I2B as a I2 value. Then this equation will become V1 is equal to here Z11A plus Z11B into I1 plus here Z12A plus Z12B into I2. So this is equation for the input voltage equation of the resultant network. Then similarly substitute the V2A and V2B values in equation number 7. Okay, so that, because here this is the again simplify, then you will get finally that V2 is equal to here Z21A plus Z21B into I1. Okay, and Z2A plus Z22A plus Z22B into I2, right? So let us write the equations for the resultant network. So the equation for the resultant network is here, because the input voltage and input current for the resultant vector is V1 and I1, and the output voltage and output current as V2 and I2. So here the Z parameters are voltage equations in terms of the current. So that's why here V1 is equal to Z11 I1 plus Z12 I2, and V2 is equal to Z21 I1 plus Z22 I2. Okay. So then compare these two equations of V1 and V2 with this equation and the previous equation. Okay, so then he will get to know, okay, so suppose here this is the V2 equation and this is the V2 equation. So in place of here, this is then Z21 and this is Z22. So which means here Z21 is equal to, here this Z21 is equal to this one, and Z22 is this equation, right? So here Z21 is Z21A plus Z21B and Z22A and Z22B. Similarly, here Z11 is equal to Z11A plus Z11B and Z12 is equal to Z12A plus Z12B. Okay. So from this, finally, we can simplify this. So Z is equal to ZA plus ZB, which means, so if the two port networks are connected in series, then the resultant vector Z is equal to ZA plus ZB. Okay. So suppose if there is a third vector, then plus ZC. Okay. Then fourth plan plus ZD. Okay. Plus and so on. So if two or more networks are connected in series, then the resultant vector, okay, sorry, the resultant network Z parameters are the sum of the individual network Z parameters. So which means Z is equal to ZA plus ZB plus ZC plus and so on. So that is what here the overall Z parameters matrix for the series connected two port network is simply the sum of Z matrices of each individual two port network connected in series, right? So then now we no need to derive the equation. If you can find the two port networks are connected in series, then the resultant two port network Z parameters are the sum of the individual two port networks connected in series, right? Now coming to the parallel connection, right? So again here the best suitable what is that what is the two-port network for the parallel connection is the admittance parameters. Okay, so that's why here we have considered the admittance parameters. So here again in this case, as you can see, again we are considered the two different networks, and let us consider the admittance parameters of the network A is YA, and the admittance parameters of the network B is YB. Okay, so the same way here the input voltage and input currents for the network A are IA1 and I1A and V1A, and the output voltage and output currents are V2A and I2A respectively. Then similarly for the network YB, the input current and input voltages are I1B and V1B respectively, and similarly the output voltage and output currents are V2B and I2B respectively. Then the resultant two-port network here let us consider as the same like in the previous case. So let us consider here Y is the resultant two-port network of the parallel connection of these two ports networks, and for the input voltage currents are V1 and I1, and here output voltage and currents are V2 and I2. Okay, so here as we know the admittance parameters, so here the current equations are in terms of the voltage. So that's why here the same way like in the previous case, so let us write the admittance parameter equation for the network YA, so which is I1A and I2A in terms of V1A and V2A. So the same way, I mean this matrix form, let us write into the equation form. Then let us consider here equation number 1 and 2. So equation number 1 and 2 represents the admittance parameter equations for the network YA. Then similarly for the network YB, okay, so the same way here, because the input current and output currents for the network YB are the I1B and I2B, then let us write the equations for the admittance parameters for the network YB. Then the equations are I1B and I2B. So let us consider here I1B is equation number 3 and I2B is the equation number 4, right? So now let us write the condition for the parallel. Okay, so the condition for the parallel is if two or more networks are connected in parallel, then the voltage across each network is equal to each other, right? So that's why here V1A is the input voltage for the what is that network VA, and V1B is the input voltage for the network YB, so that here these two are equal to the resultant voltage vector V1, because all are connected in what is that parallel. So similarly the output voltages for the network A and network B also same as with the resultant vector output voltage V2, right? And as we know, if these two are connected in what is that parallel, okay, so by applying the KCL, so we can get the equation I1 is equal to I1A plus I1B, and similarly I2 is equal to I2A plus I2B, right? So then now substitute the values here, okay, so you can see here I1, then substitute I1A and I1B values in this equation number 1, okay, I mean in this equation. So here I1A and I1B values in the first equation. So I1A and I1B values. So I1A is here. This is I1A from the equation number 1. Okay. And I1B from the equation number 3. Right. So substitute the equation number 1 and 3 in this particular equation. So that, okay. Then substitute here I1A is equal to Y11A V1A plus Y12A into V2A. And similarly here I1B is equal to, so this here we have substituted, then Y11B into V1B plus Y12B into V2B. Then if you simplify this, then you will get finally, because here we should write the what is that, the current equation in terms of the voltages. Okay, so the current equations are I1 and I2 for the resultant network, and the voltages are V1 and V2. So that's why we should write I1 and I2 in terms of V1 and V2. So for that here we are simplifying, and then finally we are just make sure that the equation of I1 is in terms of V1 and V2. Of course here as you can see, so the I1 is equal to, okay, so this Y11A plus Y11B into V1, and Y12A plus Y12B into V2. Okay, so let us consider this is equation number 6. Then similarly, the same way substitute the values of here I2A and I2B in this equation. Okay, in this equation, then you will get the I2 value as Y21A plus Y21B into V1 plus Y22A plus Y22B into V2, right? Then compare these two equations with the standard equations of I1 and I2. So I1 and I2 is equal to y11 v1 plus y12 v2, and I2 is equal to y21 v1 plus y22 v2, right? Then compare these two, then you will get finally here y11 is equal to y11a plus y11b, and y12 and y121 and y22. So from this relation, you can conclude that, so even though admittance parameters, okay, those are in connected in a, what is that series, okay, sorry, those are connected in parallel. So again, the admittance parameters y is equal to, okay, so ya plus yb. So in case of the parallel connection also, the admittance parameters, the resultant network admittance parameters is equal to the sum of the admittance parameters of the individual networks, right? So this is how, how to find the parameters of the resultant network, right? About the parallel connection. Then coming to the cascade connection. So the cascade connection is nothing but the output terminals of the port 1 are the input terminals for the port 2, like this. Okay, then we can call it as a cascade connection, right? So the best suitable parameters for the cascade connection is the transmission parameters, which are also called as a ABCD parameters. So that's why in this case we have considered the ABCD parameters to find the parameters of the resultant network, right? So here also let us consider the network A and network B. So the transmission parameters for the network A are the TA, and the transmission parameters for the network B are the TB. Okay. So first let us consider the network 1 or network A. So for the network A, write the transmission parameter equation. So the transmission parameter equations are the input voltage and input currents are in terms of the output voltage and output currents. So for the first network here, the input voltage and input currents are V1 and I1. So that's why here we have written the equations of V1 and I1 in terms of the output voltage, which is V2A, and the output current is I2A. So then V2A and I2A. So then if you write this into the equation form, then you will get V1 and I1 equation. So let us consider this is equation number 1 and this is equation number 2, right? So now similarly, we can write for the second network. So for the second network, the input voltage and input currents are V1B and I1B, and the output voltage and the output currents are V2 and I2, right? So now the equations are V1B is equal to A2V2 minus B2I2, and I1B is equal to C2V2 minus D2I2, right? So let us consider these are equation number 3 and 4. So from the figure, okay, so we can able to know, because when coming to the currents here, because here this current are both are connected to this terminal, which means the current flowing through this particular is same, but the directions are opposite. So that's why here I1B is equal to minus I2A. So this relation we can make from this particular network, right? Then similarly here V2A is equal to I2B, because here the voltage across these two terminals is same. So here the voltage across the output terminals of the network A is V2A, and the input voltage for the network B is V1B. So that's why here V2A is equal to V1B. Okay. Then substitute these values in equation number 1 and 2. So here the equation number 1 is the input voltage and input currents for the network A. Then substitute the values of here the V2, wherever the V2A is there, then substitute V2A as a V1B. So that's why here V1B that they have substituted. And here I2A, in place of I2A is here minus I1B. So here that's what here they have substituted, so that here the minus minus gets plus. Then similarly here I1 is equal to V1 into here V2A, again in term where V2A is replaced with V1B, here V1B, and again here I2A, so I2A is replaced with minus I2A, so, minus I1B, so minus I1B. Then the equations of V1 and I1 are in terms of A1 V1B plus B1 into I1B, and I1 is equal to C1 V1B plus D1 into I1B. Then the same way, put the V1B and I1B values in the above equation. Okay, V1B and I1B, because V1B, I1B values here we get from equation number 3 and 4. Okay, then substitute the equation number 3 and 4 in equation number, which one? Okay, let us consider, we didn't consider, but in the above equations, then here, wherever the V1B is there, so here V1B is equal to A2 V2. Okay. So here this is substituted here. So this is V1B, okay, and this is here I1B, okay. Substitute these values. Then simplify. Then you will get V1 is equal to A1 A2 plus B1 into C2 into V2 minus A1 B2 plus B1 into D2 into I2, because here we should write the input voltage and input current, that V1 and V2 equations in terms of I1 and V2 and I2. So that's why we have done this thing. Then the similar way, here also substitute, okay, that V1B and I1B values in this equation. Then you will get finally this one. So here this is the input voltage and input current equation in terms of output voltage and output current equation for both V1 and I1. Then for the equivalent network, okay, the equations are V1 is equal to A1 into V2 minus B into I2, and I1 is equal to C into V2 minus D into I2. Then comparing equation number 5 and 6 with the standard equation, then you will get here A1 is equal to, A is equal to A1 A2 plus B1 C2, and B is equal to A1 B2 plus B1 D2, and similarly C and D values, right? So from these equations, then if you write into the matrix form, then you will get finally the equation is like this. So when you, if you simplify this, here it is A1 B1 C1 D1 and A2 B2 C2 D2. So which means finally the transmission parameters or the resultant transmission parameters is equal to the product of the individual network parameters. So that's what the T is equal to TA into TB. So this is about the cascade connection of the two networks, right? So finally we can conclude that if the two or more networks are connected in parallel, then the best suitable network parameters are the Y network parameters or the admittance parameters. Then in this case, the resultant network parameters Y is equal to the sum of the individual network parameters, that is YA plus YB. And similar way, even coming to the series connection, okay. So for the series connection, again, but the best suitable parameters are the impedance parameters, which are Z parameters. So then the resultant network parameter Z is equal to the sum of the individual network parameters, which is nothing but ZA plus ZB. And when coming to the cascade connection, so the best suitable network parameters are here the transmission network parameters. So for this transmission network parameters TA and TB, okay, so then the resultant network parameters, the resultant vector transmission parameters is equal to the product of the individual network transmission parameters, which are TA and TB, right? Then now let us take one numerical problem to understand better about these two networks. Okay, so here compute the Y parameters of the network shown in figure. So of course here this network, when the Y parameters are possible, if the two networks are connected in parallel. So here these two networks are connected in parallel. So now we are going to find the Y parameters for these two networks. Okay. So to find the Y parameters of the resultant network, so first we should find the Y parameters for the network 1 and the network 2. So let us consider here this is network 1 and this is network 2. So first to find the Y parameters from this network. So here, as we know, here directly we can find the Y parameters by equating this network into the equivalent networks. So the equivalent network for the Y parameters that we have already discussed in the previous classes. So it is like this, that is Y12 and Y11 plus Y12 and Y22 plus Y12. Just to compare with these, then here y12 is equal to, in the place of y12, what you are having here z4, so minus z4, and which is equal to here y21a also. And similarly, in the place of y11 plus y12, here we will be having 2s, so that's why here we have just placed as a substituted as a 2. And in the place of y22 and y12, here we are having the 3. Okay, so that's why here we just indicated as a just compare and write the values. Or we can also write this one, okay, into, okay, we can also write this one into like from this, okay, what is that here, y12 and y21, okay, and here y11 is equal to 2 plus 4 j4, and y22a is equal to 3 plus j4. Then write this into the matrix form. Then the admittance matrix for the network A Okay, the admittance matrix for the network A, so which is YA is equal to 2 plus J4 minus J4 and minus J4 and 3 plus J4 into S. Then similar way for the network B also, if you can, if you write the equations, okay. So here y12b and y2b is equal to minus 4 because here the 4 is there, and here y11b is equal to 4 minus j2. Here 4 is there and minus j2, and y2b is equal to 4 minus j6 because here minus j6. And write this equation also in the, in matrix form, so that yb is equal to this one. So already we know when the two or more two port networks are connected in parallel, then y is equal to ya plus yb. So here we know ya and yb. Just add these two matrices, then you will get the resultant matrix y parameters. Then here the y11 which is equal to 6 plus j2, and y12 is equal to minus 4 minus j4, and similarly y21 is equal to minus 4 minus j4, and y22 is equal to 7 minus j2. So in this way you can find the what is that the two port network parameters for the resultant circuit when the two or more networks are connected in parallel. The same way you can also find the two or more networks are connected in series and the cascade connection, right? So this is how all about the interconnection of the various two port networks. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.